Hello and welcome to the fourth and final video of the FP1 chapter, Transformations Using Matrices. Question on the screen here, just to review what we did in the last video. Write down the matrix that represents a stretch in the x direction of scale factor 4 and a stretch in the y direction of scale factor half. So in the x direction we need a 4 times bigger, and in the y direction we need it a half times bigger, and there we go. This final video in this chapter is going to squeeze two things together because the idea of both of these is quite straightforward, although there are a few examples. So first we're going to apply successive transformations, and then we'll look at reversing transformations. To apply multiple transformations, we can combine the matrices with matrix multiplication. But as is always the case, the order of the multiplication is very important. The transformation TU, so this is one transformation and this is another transformation, the combined transformation represents the transformation U first, followed by the transformation T second. Now that's a little bit unintuitive because we normally read from left to right. It looks like T comes first. But because when we're applying transformations, let's say we've got a matrix that's got some coordinates, maybe 3 points, 2 coordinates each, and you want to apply the matrix U onto this matrix of coordinates, then you want to apply T. So because U is closer to the matrix of the coordinates, it happens first. Then T is applied second. But you also know that it doesn't matter where the brackets go so long as the order of the matrices stays the same. So that is the same as this. And this says I can combine these two matrices into one matrix that has the same effect, but it is still the effect of U happening first and then T happening second, even though it will be a combined matrix. So that's very, very important. Here's a quick example. Find the 2 by 2 matrix T that represents a rotation 90 degrees anti-clockwise, about 0, 0, followed by a reflection in the y-axis. But don't panic, I'm not going to use that rather horrible rotation matrix. I'm going to just consider what happens to our old friends, this and this. And if I want to rotate these anti-clockwise, if I want to change the yellow one so that it's here, that needs to be a 0, 1. And if I want to rotate the blue one so that it's here, that will become a -1, 0. So because it's a 90 degrees, it's quite an easy number. When you put it into sine and cosine, you get these answers here. And that needs to be followed by, so the next matrix goes on the left of this, because the matrix of coordinates would go over here. So this one first, followed by this one, is a reflection in the y-axis. So the y-axis reflection, the yellow one would end up over here. So that would be a -1, 0. And the blue one wouldn't change, so that would be a 0, 1. Now the matrix T that represents both of these, this one first and this one second, is just the multiplication of these two in this order. So to find that, I go ahead and do the multiplication, and I get 0, 1, 1, and 0. Part B, describe the single transformation represented by T. Okay, well we're going to do basically the same thing. Let's have a look at what happens to the yellow one. The yellow one changes to 0, 1, which is where the blue one is now. And the blue one changes to 1, 0, which is where the yellow one is now. So they swap places. And for that to happen, it must be a reflection in the line y equals x. So T is a reflection in y is equal to x. Obviously T is also this rotation followed by this reflection, but that word single is very important. The single transformation represented by T is this. To show that the order is very important, we've got almost the same example, but I'm going to switch these around. Find the 2 by 2 matrix T that represents a reflection first, followed by a rotation second. So again, my general approach is to consider what happens to this and what happens to this. So a reflection in the y-axis first, we had -1, 0, 0, 1, followed by the rotation second, so on the left, 0, 1, -1, 0. This is now t in this example, and that gives us 0, -1, -1, 0. Different. Of course, you should remember that it won't always be different, but you should never assume it will be the same. There are some transformations where if you change the order it doesn't matter, but generally you should assume that it does matter. Here, describe the single transformation represented by this t. Again, let me just consider what happens to the yellow one. That changes to 0, -1 down here, and the blue one changes to -1, 0 here. So in order to get this one here and this one here, what has happened this time is a reflection, but not in y equals x, in y equals -x. So a subtle difference there, but an important difference. Here we've got A is equal to this mess, representing an enlargement with scale factor k, followed by a rotation of theta anticlockwise about 0, 0. This one's a little bit more of a problem-solving question, and is quite a nice example in the textbook. We need to find the value of k, the enlargement, and find the value of theta, but there's no easy way to see how to split these two to get this result when you combine them. What we do know, let me write it out like this, the scale factor k looks like this, and a rotation theta anticlockwise, now we do want to remember that horrible mess, is this. And these two together must make the thing we've got given to us in the question. Now what you could do is do this times this plus this times this makes this, and this times this plus this times this makes this, and then solve your simultaneous equations, and that's fine, you can do that. But what I'm going to do here is give you a little clue as to how useful the determinant is, because if we know that this is an enlargement, then the scale factor of the area is k squared. Now this is useful to know because when you do the rotation or a reflection, but the rotation in this example does not change the area of the shape. The only thing that changes the area of the shape is the enlargement. So if we find the determinant of this matrix, that will be the area scale factor. And then we can just square root that to get the scale factor k, which tells us what this matrix is. So the determinant here is this times this minus this times this. So the first one is minus 2 root 2 times minus 2 root 2, that's 8, and minus 8, 16, which is a very nice number to have for k squared, because it means k is 4. And now we will do what we had before, the idea of just going ahead and doing this times this, so 4 cosine theta plus 0 must equal this. So we've got 4 cosine theta must equal minus 2 root 2. And let's take a sine theta as well. So let's have 4 sine theta plus 0 must equal 2 root 2. And this one would give us the answer 45 with the second answer of 135. And this one would give us the answer 135 and 225. So we can see the agreement here is that theta must be 135 degrees. And there we have our two answers. So there are a couple of examples about combining transformations. But just to finish this chapter off, we can also reverse the effects of a linear transformation by using the inverse matrix of whatever the transformation matrix was. And it's worth noting that this result here is a really good one to remember. This is equivalent to saying that the last transformation, here A, remember the one on the right is the transformation that happens first, then the one on the left. And when you want to undo that, when you want to invert that, you have to undo the last transformation first. This is a little bit like saying if I put on my socks and then I put on my shoes, I have to take off my shoes before I can take off my socks. So the last one must be undone first, which is why this is such a useful result. Here is our final example, and then we will finish. The matrix M represents a transformation T, and that might seem really strange. We've assigned this thing 2 letters, M for the matrix, representing T the transformation. Unfortunately, that's quite a normal thing to do, although it can get quite confusing for people. The transformation T means the matrix M. So given that T maps point P onto the point P prime using the matrix M, find the coordinates of P. Okay, so it's saying basically 2, 4, minus 2, minus 5 applied to x, y gives you the answer 6, 10. Now there is a bit of a choice here, because from a previous example we've done, you could easily say, well, why don't we just make simultaneous equations? 2x plus 4y must equal 6, and minus 2x minus 5y must equal 10. And that's not a bad way of doing this. In fact, when you get to FP3, if you do that module using 3x3 matrices, that's actually a much quicker way of doing it than to find the inverse matrix of a 3x3 matrix, which is effectively what I'm going to do here with the 2x2 matrix. The reason I maybe wouldn't do it here is because finding the inverse of a 2x2 matrix isn't that difficult. So instead of multiplying this out and solving the simultaneous equations, I'm going to do what the question kind of wants me to do, which is to say, if I do the inverse matrix of this, then I can take it over here, remembering our matrix algebra. This is like saying M times P equals P prime, and if I want to get rid of M to find just P equals, this is what I want to finish with, then I do the inverse on the left of this expression, and I have to do the inverse on the left of this expression, and of course this becomes I, which has no effect on P. So if I can find the inverse matrix, I multiply it by the one I know, P prime, 6, 10, and that will give me the result, P. But like I said, for a 3x3 matrix, that's actually quite a lengthy process, and you would just do the simultaneous equations. But here I will follow through. So the inverse matrix of M, we need to know the determinant first. The determinant, 2 times minus 5 is minus 10, minus 4 times minus 2, so that's a minus 8, minus 10 plus 8 is minus 2. So the inverse matrix is 1 over the determinant, times by A and D must swap places. And then these two stay where they are, but they get negatives put in front, so that's a minus 4, and this becomes now a plus 2. So the inverse matrix becomes 5 over 2, 2, minus 1, minus 1. And I'm multiplying that on the left of this expression, 5 over 2, 2, minus 1, times by 6, 10, will give me the answer x, y. 15 plus 20 is 35, minus 6, minus 10, minus 16. And hopefully if you do the simultaneous equations method, you get those same answers. So P is 35 minus 16. Part B, the matrix N represents a transformation U. So again, these two things are effectively the same thing, but we're calling this the transformation, and we're calling this the matrix representing that transformation. Given that the transformation T followed by the transformation U, so that's T first followed by U, is equivalent to a reflection in the line y equals x, find n. So this is where the notation might get a bit confusing. We want T followed by U. I've written it like this to help show what I'm going to do, but these are not matrices, these are the transformations represented by the matrices. So what I'm actually going to be using is M followed by N, but it's kind of the same thing. So this matrix combination is equivalent to a reflection in the line y equals x. Now the matrix for the line y equals x, if I have my little diagram again, what happens here and what happens here needs to be a reflection in the line y equals x. So the yellow one would end up becoming the blue one, which gives me a 0, 1, and the blue would turn into the yellow, which is a 1, 0. So these two must combine to give this matrix. And I know what n is, so we've got n, the thing we don't know, times m, the thing we do know, must equal 0, 1, 1, 0. And here is where the simultaneous equations approach would be a bit more difficult, because n is going to have 4 unknowns, a, b, c, d, and that would be a much more complicated process to do. So let's stick with our matrices. Remember our algebra. Let me call this combination matrix R. Then to get rid of m on the left, I need the inverse of m on the right of the expression. And that becomes an I, so times that by n is just n. So R times the inverse of m, not the inverse of m times R. And if I can remember what the inverse of m was, we've just got a multiplication and then we're done. So R is 0, 1, 1, 0 times by 5 over 2 to minus 1, minus 1, which is minus 1, minus 1, 5 over 2, 2. And that must be the matrix N. Now I hope that's been enough for you to have a go at the remainder of the questions in the chapter. 6D for combining successive transformations, 6E for reversing transformations using inverse matrices or simultaneous equations, and the chapter 6 review exercise to practice all of these ideas before we move to chapter 7, which is very different, talking about series. Maybe I'll see you there.